Okay, so if we can describe our balanced three-phase system, right, there are a couple of different ways that we can make three-phase connections. And we describe them by describing the source, its three-phase connection, to the load, its three-phase connection. Again, this is why I get a little confused sometimes, because there's 4 different configurations and they use very similar terminology, so I have to be really careful, right? But there are 4 possible ways of making a connection. I could have a Y-connected source connecting that to a Y-connected load, right? A Y-connected source connected to a delta-connected load. So just think about, again, what's the configuration of the 3 voltage supplies and then the 3 impedances that are on the other end. Finally, I could have delta-delta, or I could have delta-Y. Right? And so we're going to actually look at each of these 4 configurations to help us, figure out how can I simplify the math when I'm working with a 3-phase system. Right? So we're going to start with a balanced Wye-Wye system. So this is the way the configuration looks, right? It's a 3-phase system. My supplies are all connected to a common neutral point, and my loads are all connected to a common neutral point. The nice thing about this configuration is it allows me to connect the neutrals together. So that can be handy, again, especially if I wanted to have a ground, right? If I wanted neutral to be hooked to the ground, I can do that very, very easily in this type of a configuration. Okay. So, what else do we need to know about our configuration? We want to calculate the various components in this system. Right? So I mentioned we described the individual voltage supplies as the phases, right? But then we also talk about the connection between the power supply and the load, and we call that the line. So in this case, we want to calculate the line current in the Wye-Wye system. We want to calculate the current flowing through this wire from phase A on the voltage supply side to its corresponding point on the load. And another thing you'll notice about this configuration that's quite common in these problems throughout the chapter is that the line itself now has an impedance. So think of that like the Thevenin equivalent circuit, right? So here I have, if I'm only looking at this A branch, here I have a voltage supply with an impedance connected to a load impedance, right? So it looks a lot like the Thevenin equivalent circuit. Thevenin equivalent voltage with a Thevenin equivalent impedance connected to some load that I've chosen now, right? So if I'm describing like a power distribution system, again, I know the voltage is 110 volts coming out of the wall socket, right? And I can determine whatever the impedance of the lines getting up to that point would be, right? There's some resistance. In this case, there's a negative J2, meaning there's some small effective capacitance as well. And then I'm connecting this to an impedance that has some resistance, and since it's a plus J8, it has some inductance, some effective inductance to it. So I can determine for each one of these. Now in this case, the one challenge that I have is that the neutrals are not connected, right? So if I wanted to do my analysis on this circuit, I can just approach this by standard mesh analysis, right? Let's do standard mesh analysis for it. Let's see where this comes from. So if I do mesh analysis, I have 2 meshes, right? 2 loops in this circuit. There's this upper loop here and the lower loop here. So I'm going to do KVL around the upper loop. And I'm just going to work my way around the circuit, right? This is little I1, right? My little unknown. I'm going to start at the neutral point, just so that I remember where I'm at, okay? And we go through the circuit. I have negative 110, phase of 0, plus 5 negative J2 times my, I'm going to call that I1, plus 10 plus J8 times I1, plus 10 plus J8 times I1 minus I2, right? The current in the loop I'm in minus the current in the other loop. Plus, let's come over to the next line, 5 minus J2 times I1 minus I2 plus 110, phase of negative 120 degrees equals 0. So it's a little bit long, but it's just a KVL loop, right? And then I could write down my second equation, so I could simplify this and put all of my parts together. Again, I would use MATLAB to do most of this, but if we look at it, what am I going to have? I'm going to have, here I have a 10 plus J8 and another 10 plus J8, so I have times I1. So my I1 terms, I have 5 minus J2. Okay, let me just add the reals together. I'll go ahead and do that in my head, right? So of all of my I1 terms, I have 5 plus 10, that's 15, plus 10, that's 25, plus 5, that's 30. So I have 30. And then the imaginary terms, I have negative 2 plus 8, that's 6, plus 8, that's 14, minus 2, that's 12. And then on my I2 terms, right, I have negative 10, negative 5. So I have negative 15. And the J's are negative J8 plus J2. That's negative J6 times I2. And then if I were to move these constants to the right-hand side, I'd have to put them into rectangular form. Right. But they're going to look like this. It's just a 2x2 mesh, right? Had a lot of pieces, but in the end it's just one complex coefficient for each of the terms. And so I could do that. I could do KVL around the second loop. Right. Which we're going to call I2. If I do that, you know, you can see if I were to start here, I'd have a very, very similar equation, 110 with a negative 120 degree phase, plus 5 minus J2 times I2 minus I1, plus 10 plus J8 times now I2 minus I1, plus 10 plus J8 times I2, plus 5 minus J2 times I2, plus 110, phase of negative 240 equals 0. That is really, really similar to what I had up here, right? Because everywhere here that I had, of course, the I1 minus I2, now I have I2 minus I1. But even the other terms where I have just the I2, I have a 10 plus J8 times I2, just like I had a 10 plus J8 times I1. I have a 5 minus J2 times I2, just like I had a 5 minus J2 times I1, right? Because the two loops are the same, except for the phase difference. Because here I have a 0 and a negative 120. When I move these guys over, I'm going to have negative 120 minus the 110 with the phase of negative 240. Right. So here, I have 110 minus 110 phase of negative 120. Here, when I move this over, it's positive, so I have 110 phase of negative 120 minus 110 phase of negative 240. Right. Which we can put those together and you'll find you just have a 120 degree phase shift. There's some equivalent value. So when I solve this, right, I would get little I1 and little I2, but little I1 is the current in the A line. Right? Everybody agree with that? That is this one. And our little I2 is just going to be negative the current in the C line. Right? And then the current, of course, in this one is the difference between the two. Right? And so what we can find is that in fact the three line currents are all the same, they're just 120 degrees out of phase with each other. So if I calculate one of them, right, so if I calculate the IA, which is my zero phase to begin with, I find out that I have a negative 21 degree phase, magnitude of 6.81. So to find the next in the sequence is this one, right? Because again, A leads B by 120 degrees, now that we've settled on that terminology, right? A leads B by 120 degrees, so IA leads IB by 120 degrees. So IB is, the phase is 120 degrees less. And then the B leads the C by 120 degrees, and so again, now we have the negative 140, I can subtract 120, and then they've converted it over to being positive 98. Negative 140 minus 180. It's gone past the 180 line, so they've gone, and they described it with a positive angle instead. But the magnitudes are all the same, right? So I've solved this system just using my standard KVL. As I mentioned, you don't have to do anything new necessarily, but I don't actually need to solve this full thing because I can use the symmetry to make it easier to solve.